In this video, I will answer all of your questions about how to fine-tune the LLaMA model. Can both models generate code? Do these models use the GPU? And how much RAM is necessary to run the models? And many more questions. But before we start, I just want to say thank you for all of your kind words and incredible feedback on my last video. I really appreciate that, and it motivates me so much to keep going, and that's what I'm doing today with another video. And now let's start. I know that not all of the questions will be relevant to you, so what I would recommend you to do is to check out the description box, because I divided the video into different chapters and just pick the questions that are relevant to you, so this way you get the most out of the video. And now let's start with the first question. And the first question was about the input and output token limit of the Alpaca model, as well as how the instruction following training data was generated and how the model got fine-tuned and how we can fine-tune the model ourselves. I first want to briefly answer the question about the input and output token limit, and for this I found this open issue in the LLaMA repository, and one of the contributors states that the model was trained with 2048 tokens, so you can use up to that, and if you want to use more tokens, fine-tuning the model would be required to support longer sequences. And now let's get to the fine-tuning of the LLaMA model, and Stanford really shared everything with us, all of it. So in this repository we find all the data they used, the 52,000 instruction following tasks which they used for fine-tuning the model. So we can have a look inside and see here we have an instruction, give 3 tips for staying healthy. There is no input. An input could, for example, be that we ask the model to summarize the text, then the text would be the input, and we pass to the model the desired output so it can learn how to behave like a chat agent. What they also shared is how they generated the data, which I think is very cool, because here we can see all the seed tasks they used, and also they shared the prompt which they used to generate the instruction following tasks, the 52,000. So they used this prompt and passed it to the OpenAI DaVinci model, and in this way they generated all the 52,000 instruction following tasks which they then used to fine-tune the LLaMA model, and ended up with the Alpaca model, which is truly impressive and comparatively very easy to get there. And now finally I want to show you how the fine-tuning can be actually done, and for this we can see they shared with us all the hyperparameters which they used. Also they shared how you can run the fine-tuning, exactly how they did it. I really like their documentation. It's very easy to follow, and I think it makes it very easy to reproduce their results, which I really like. And as you can see here in the final command, you really just have to replace 3 different parameters, and then you're basically able to run the fine-tuning the way they did it. And if you ask me, I think the hardest part for fine-tuning the model yourself will be the data generation part. While looking at this, I think fine-tuning the model looks to me pretty straightforward. Regarding the fine-tuning, I have one more repository for you. By the way, if you like this video so far, I would really appreciate if you give this video a like and subscribe to my channel. And this repository is called Alpaca-LoRA, and the name LoRa comes from low-rank adaptation, which is a parameter-efficient fine-tuning strategy which allows you to instruct-tune the LLaMA model on consumer hardware. What does this mean? The authors of the repository were able to run the training or the fine-tuning within 5 hours on a single RTX 4090, and this is another time really impressive. I want to give you a few more information about the low-rank adaptation and some perks it brings, and why you should consider using this implementation for fine-tuning. And one of the reasons why the low-rank adaptation is really cool is that the authors here used the GPT-3 175 billion parameter model, and by applying the low-rank adaptation instead of fine-tuning it with Adam, so basically fine-tuning the whole model, all parameters, they could reduce the number of trainable parameters by 10,000 times and the GPU memory requirements by 3 times, and still perform on par or better on multiple models like Robot A, dBERT A, GPT-2 and GPT-3. I'm not sure if I pronounced them correctly. And I don't want to give you a deep dive into the paper, but I want to give you a broad understanding on how this is possible. And I feel like this illustration helps definitely. So imagine we have our embedding like an input vector, and think of this as a transformer in our large language model. And usually if we would do a normal fine-tuning where we update all the parameters of the model, we would also update this part of the model. But with the lower rank adaptation, what we do is we freeze all the weights in here, so we won't update the weights inside our model architecture, the existing at all. We just inject trainable rank decomposition matrices into each layer of the transformer architecture. So those are the rank decomposition matrices that are trainable. And maybe you have seen something similar. It works a little bit like an autoencoder. So we heavily reduce the dimensionality of our weight matrices inside the transformer or attention matrix. And this way we have to update way fewer parameters during training, because all of the model parameters are untouched during our fine-tuning. We just learn this rank decomposition matrices, but don't touch the model architecture overall. And in inference, we obviously add a little bit of complexity to the model, but I would guess in practice you won't even feel a difference. And during training, the authors even observed a 25% speed up compared to full fine-tuning the GPT-3 model. And finally, I want to show you why I even spent so much time explaining this all to you. So now we can see that this is our frozen model, and those are our fine-tuned task-specific weights. So if you plan to fine-tune the LLaMA model for multiple tasks, it's way easier to just swap the LoRa weights instead of swapping the whole model, because this part is tremendously bigger than this part. For example, I already found a fine-tuned version of the Alpaca 13B version, and here you can see the LoRa weights only contain 26 megabytes, where I would guess the fully fine-tuned Alpaca 13B version would have around 9 gigabytes of data. So you can see that this is way more lightweight, but also for swapping between different tasks or task-specific models. And on a final note, I want to point out that in this repository exists a clean version of the original Alpaca training data, which you can see here. And what was fixed, they described it in this pull request. They resolved some empty outputs, added a few chain of thought examples, fixed a few empty code examples, removed instructions, resolved NA outputs, make empty input consistent, and fixed a few wrong answers. So in case you're planning to fine-tune the LLaMA model with training data that was generated by OpenAI's GPT model, you might also want to check out this pull request to further improve your data quality. And this brings us to the next question: can both models generate code? And I thought before I talk much, I just show the answer to you. And for this, I found the following instruction in the Alpaca-LoRa library, which states: write a Python program that prints the first 10 Fibonacci numbers. And as we can see, there are different prompts or results for the Alpaca-LoRa, Stanford Alpaca, and the TextDaVinci 3 model. And what I then did is just copy the prompt, paste it in the DALI web interface, and see what it generates. And as we can see, the result is not really satisfying. And this got me thinking, wait a minute, something looks wrong. Because in the Alpaca-LoRa repository, they state that both models, the Alpaca-LoRa and the Stanford Alpaca model, and both are able to generate a Python program. So I was thinking, why is that not possible in the DALI interface? And what I then found is that the official model weights of the Alpaca model aren't even released by Stanford. So they intend to release the model weights in the near future. And on a side note, also the one for fine-tuned version of the larger LLaMA models, which is really cool. So not just the 7B, but that's just on a side note. And what I was then thinking is, which version of the Alpaca model got even quantized, and which version are we actually using? And to further investigate the capabilities of the LLaMA model, I just decided to go with the Alpaca-LoRa repository and check out if I can generate code with the model version that they released. And since this repository is not quantized and runs on a GPU, I created a Colab notebook where I cloned the repository. I had a minor issue with the RJSON library when installing the requirements, so I had to install an older version, but maybe at the time you're trying this, you don't have to do this additional step. I also commented it here, and then I proxied the port so we can access our local running Gradio app using this link. And finally, you just have to run this cell, and then you can click on this link and access the Gradio interface. And then finally, I pasted the instruction again, executed the prompt, and here's my result. And I know that some of you commented that you're not happy with the results of the Alpaca model and it's not even close to the ChatGPT model. And now that I see that there's a difference between the output I'm getting in this Gradio app and in the DALI interface, that we might not using the original weights, or something went wrong with the quantization of the Alpaca model. And here's what I found regarding the LLaMA C++ file, and the author or the owner of the repository wrote the following thing. This was hacked in an evening. I have no idea if it works correctly. Please do not make conclusions about the models based on results from this implementation. For all I know, it can be completely wrong. This project is for educational purposes. New features will probably be added mostly through community contributions. And in another thread, he also mentioned that the downside is that he haven't had the chance to compare the outputs at different stages of the inference, so he has doubts himself about the correctness of this implementation. And maybe we have encountered here that the code generation in a quantized model version is not as good as in the original fine-tuned model version. But I definitely don't want to leave a bad word about this repository, because I think this is a very promising project, because if we were able to run those big models on a CPU, those large models can be made available to so many more people. So I hope that there will be a solution found, because if we were able to run those large models on our CPU, that is really cool. And to finally answer the question, yes, both models can generate code, but it seems like the quantized version is not as good as the original model version, which we would run on a GPU instead of a CPU. So let's hope that this can be fixed in the future, and then we can also run the CPU version on our local computer and also generate code with this. And this brings us to our next question. Do these models even use or benefit from GPUs? And the answer here is no. The inference is really computed only on the CPU, so there's no need for a GPU if you use the DALI library. But as I showed you in the question before, there's also a way to run those models with a GPU. And as for now, it seems that those models work better than the quantized version. But I hope that will be solved soon. Next question. How much RAM is recommended to run the individual models on your computer? And here I found this piece of information where you can see the recommended RAM on your computer for each model variant. One user has stated though that for the 30 billion parameter variant he even needed 24 gigabytes of RAM. And here's another question. Does the model work with languages other than English, like Spanish for example? And the answer to this can be found in the LLaMA paper. And here we can see that the model was trained using various datasets, and only the Wikipedia dataset consists of multiple languages, which are in total 20. So the foundation model has seen different languages, but of course the best results you will achieve in English language. So I think to really get great results, a fine-tuning would be needed. And one more thing, the Alpaca model, as we can see in the prompt to generate the training data, the instruction should be in English only. So the Alpaca model will be even more specialized on English language. So don't expect great results in languages other than English using the Alpaca model. All right, another question. Could we use this to query a database using natural language? And the answer is not yet, but the Alpaca model is already able to generate SQL code. But I could imagine that further fine-tuning the model with SQL data would definitely improve your results. And right now the model can just respond to you, but can't really actually query a database. But I'm planning to cover in future videos how these broad large language models can be combined with domain expert models. So if you're curious about those topics, feel free to subscribe to my channel, so then you don't miss out on my future videos about that. And I got even more questions of you guys, and that's why I decided to create a Medium article where I answer even more questions additional to this video, because I feel like some questions can just be answered faster in written form. And here you can see all the questions that are answered. There are also questions that I didn't cover in this video. For example, why does the model generate random character sequences? So if your questions haven't been answered in this video, maybe check out the document. For me, it's also an easier way to keep the document updated with future questions, because I can't really update the video, but updating the document is quite easy for me. And yeah, that's it for today's video. One more time, thank you for your incredible feedback on my last video. I hope today you learned even more about the Alpaca and the LLaMA model. If so, as always, I would appreciate if you give this video a thumbs up. Also, if you would subscribe to my channel. And until then, have a great time and see you in the next video. Bye bye.